Hey everyone, and welcome to this explainer. I'm your host. Now, as a computer science teacher who's been preparing students for Cambridge IGCSE and OCR A-level exams for, well, over 25 years now, I can tell you for a fact that this specific topic is exactly what separates the top-tier A grades from the rest of the pack. Today, we're unpacking Section 1.2.1 Operating Systems, and my goal, to break this down so clearly that you'll literally be answering these exam questions in your sleep. So, here's our game plan for today. We're going to start by looking at the master controller, then move right into managing memory and space. After that, we'll tackle CPU scheduling algorithms, handle interrupts, decode the BIOS and device drivers, and finally, we'll wrap things up by exploring virtual machines. Let's dive right in, shall we?
Section 1. The Master Controller. Purpose and Types of Operating Systems.
To really wrap your head around what an operating system actually does, I want you to imagine a massive, highly complex factory. The operating system, well, it's the ultimate factory manager. Notice how it sits right there in the middle, acting as this perfect bridge between the user applications at the top and the raw, physical hardware at the bottom. The OS doesn't actually build the products, right? But it completely takes the burden off software developers so they don't have to stress about the literal physics of spinning hard drives every time they write an app.
The absolutely crucial point here is this. Without an operating system, a computer is essentially just an incredibly expensive, totally useless paperweight made out of silicon and plastic. The OS completely hides the sheer complexity of the hardware from the user, and it manages all the system's resources securely and super efficiently behind the scenes.
Now, OCR absolutely loves to ask for examples of different operating environments, so I highly recommend you grab a screenshot of this list right now. There are several types of operating systems you definitely need to know. We've got single-user systems, multi-user systems that actually let multiple people access a mainframe all at the same time, and real-time systems. Real-time systems are absolutely critical for things like, say, airplane autopilots, where missing a processing deadline could literally be fatal. We also have embedded systems for specialized devices like your microwave, distributed systems that share the processing load across multiple computers, and of course, multitasking systems, which is exactly like the one you're probably using to watch this explainer right now. Section 2. Managing Memory and Space, Paging, Segmentation, and Virtual Memory. Okay, let's look at how the OS actually manages its warehouse space, which in our case is your RAM. Notice the two main strategies we have here. Over on the left, we have paging. Paging divides memory into fixed-sized physical blocks. It's rigid, sure, but it is highly efficient. Then on the right, we have segmentation. Now, segmentation divides memory logically into varying sizes based on exactly what the program needs. The big takeaway? Both of these methods exist to prevent programs from accidentally crashing into each other's memory space.
But hey, what happens when our warehouse gets completely full? Because trust me, it happens. Well, that's exactly where virtual memory comes into play. Think of this as a sort of overflow parking lot just outside the main warehouse. When your RAM is totally maxed out, maybe because you have 30 browser tabs open at once, the OS takes inactive programs and temporarily pages them out to your hard drive. When you finally click back to that old tab, it swaps it back into RAM. It's a total lifesaver, even though, yeah, it is significantly slower than using physical RAM. Now, lean in for a second, because I'm going to give you a massive hint for grabbing some really easy marks on memory management questions. The OS doesn't just blindly guess where things are. It keeps a meticulous, detailed ledger. Page tables record exactly which processes are currently located in RAM or if they're parked out in virtual memory. Literally just mentioning the phrase page tables in your exam answer shows the examiner that you truly understand the deep mechanics of memory management.
Section 3. CPU Scheduling Algorithms, Maximizing Throughput.
You can think of the CPU like a master chef in a crazy busy restaurant, and the OS is the head waiter constantly organizing the order tickets to totally eliminate deadlock and starvation. To pull this off, processes are constantly swapping between three specific states. They are either running, meaning they currently have the chef's full attention, blocked, meaning they're waiting for ingredients like a file download to finish, or they are ready to run, just sitting patiently in the queue. The OS pauses and resumes these tasks flawlessly using something called a process control block, or PCB. So how exactly does the OS pick who gets to go next? Well, we have a few different strategies for that. Round robin gives every single process a tiny equal slice of CPU time. First come, first served is exactly what it sounds like, a super simple queue. Multi-level feedback queues actually create VIP lines for the most important tasks.
Shortest job first knocks out the quick, easy tasks early on. And finally, shortest remaining time constantly reevaluates which active task is closest to actually crossing the finish line.
Section 4. Interrupts and the FDX cycle. Handling emergencies.
Okay, imagine a fire suddenly breaks out in our perfectly scheduled factory. We absolutely need a system for handling emergencies, right? That is an interrupt. It's an electronic signal sent directly to the CPU to demand immediate, drop-everything attention. This could be something simple like a timer going off, or you moving your mouse, or it could be a critical hardware failure like your battery suddenly dying. Let's look at how this directly builds into the very core of how a computer works, the fetch, decode, execute cycle. At the very end of every single execute cycle, the CPU takes a tiny pause to check for interrupts. If it finds one that actually has a high enough priority, it follows these exact steps. Step 1, the current process is suspended, and its state is saved safely away into that process control block we talked about. Step 2, a very specific piece of code called an interrupt service routine, or ISR, is run to handle the emergency. And then step 3, once the emergency is totally sorted out, the original process is restored from the PCB, and it just carries on as if absolutely nothing happened.
Section 5. BIOS and device drivers. Talking to hardware. So how does the operating system actually communicate with the physical components of the machine? Well, it all starts before the OS even wakes up. Here is another major exam tip for you. The BIOS, or Basic Input-Output System, is firmware stored safely on ROM. It's literally the very first piece of software the hardware looks for the second you press that power button. It runs a quick power-on self-test, and then it hunts for the operating system loader to actually kick the whole shebang off.
Now, once it's up and running, the OS relies heavily on device drivers. Think about it. When you plug in a brand new USB drive, the OS doesn't just inherently know how to write data to that specific piece of plastic and metal. Device drivers act as translators. They contain the specific interrupt service routines and precise instructions needed to control those exact external devices. And when we're transferring data to these slow physical devices, the OS uses buffers. Buffers are basically just small areas of memory that act as a waiting room for data. This is absolutely crucial because, remember, your CPU is millions of times faster than your hard drive. By chucking the data into a buffer, the CPU can just fire it off, trigger an interrupt when the buffer is finally empty, and go perform other tasks. This ensures it never wastes its precious processing time just sitting around waiting for a slow physical drive to spin.
Section 6. Exploring Virtual Machines. System Emulation.
All right, examiners absolutely love testing this final topic. What happens when we use software to abstract the hardware entirely? Well, they come in two main forms that you absolutely must know how to differentiate. First up, we have system virtualization. This is where an entire operating system is virtualized on a host PC. Think of running a full version of Windows inside a little window on an Apple Mac. The software is literally tricking the guest OS into thinking it has its own dedicated physical hardware. Second, we have process virtualization. This is when a virtual machine is used to execute intermediate code, like Java bytecode. This is incredibly powerful because it allows a developer to write their code just once, compile it into intermediate code, and then run it on any machine in the world that happens to have the right virtual machine installed. And just like that, that brings us to the end of this incredibly crucial topic. To finish up, here is a classic 6-mark exam challenge for you. Can you describe how a distributed OS works and how it uses microkernels? I highly suggest writing out a model answer right now to really lock in that knowledge. But before you go, I want you to think about this. As our internet speeds get faster and faster, approaching the actual speed of computer buses, will we eventually see a world where the operating system of your personal computer isn't in your room at all, but rather distributed seamlessly across thousands of machines globally? Keep practicing, stay curious, and I'll catch you in the next explainer.